Hi everyone, this is Haoran from the Hong Kong University of Science and Technology. I will present our work titled PiP, Planning-Informed Trajectory Prediction for Autonomous Driving. Predicting the motion of surrounding vehicle is critical for self-driving planning in a socially compliant and flexible way. For autonomous driving systems, the relationship between the planning and prediction module is shown in this figure. To achieve real-time driving, most vehicle motion planners follow the sampling-based approach. First, roll out candidate trajectory fastly, and then score them with some policies and user-defined functions. Finally, select the optimal one to execute. The role of prediction module is to fit the future prediction of dynamic objects to planning module so as to evaluate the candidate plans more precisely. The traditional manner of prediction is only based on tracking results decoupled from future planning. That's to say the predicted future is inferred only from historical information, and thereby the same for different ego's plans. However, the future plan of controllable ego agent will largely affect the behavior of surrounding agents. It leads to a significant difference in future predictions. Then it comes to the motivation behind this work. We propose planning-informed prediction that incorporates the ego vehicle's future planning in prediction process. It produces predictions one-to-one corresponding to the candidate future trajectories of the ego vehicle. This pipeline covers how the other vehicles will interact with ego vehicle if the ego vehicle executes any specific planning trajectory. Therefore, it's especially suitable for planning dense and highly interactive traffic. Here is an overview of the PiP architecture. To effectively achieve planning-informed prediction, we propose two modules, namely Planning Couple Module and Target Fusion Module. The Planning Couple Module extracts the interaction features with a special channel for injecting the future planning, while the Target Fusion Module encodes and decodes the tightly coupled future interaction among agents. For Planning Couple Module, it has three encoding branches stemming from LSTM hidden states of all trajectories. We take the target marked with an ellipse as an example. The target's dynamics property is encoded in the lower branch. The spatial relationship between the target and its surrounding agents is captured in the middle branch. Their history motion encodings are placed into a target-centric spatial grid, termed as observation tensor. Similarly, in the upper branch, the encoding of the ego vehicle's future planning is placed into another spatial grid to form the planning tensor. Finally, all these branches are merged to form a target encoding. Next, the target fusion module is presented to capture the interdependency between target agents further. Since the future states of targets are linked up together with the planning of the controllable agent, we further fuse the encoding among different targets in the scene by applying a fully convolutional structure and decode the final trajectory from the fused encoding, which better captures the dependency of future states of different targets in the same scene. To address the inherent multimodality nature of the driving behaviors, we apply the maneuver-based decoder in the decoding part. It outputs the trajectory under each maneuver together with the maneuver probability. We modify it to operate in a residual learning manner that outputs displacement between predicted locations instead of absolute location. Accordingly, the prediction result could be represented by bivariate Gaussian distribution. The model is optimized by the posterior probability of all target vehicles' future trajectories. We compare our model with deterministic and stochastic methods on NGSIM and Heidi vehicle trajectory dataset. As a stochastic method, social gain and METF sample trajectories without generating probability. They do not have NLL results, and their RMSE is reported by the minimal error from sampling 3 times. The result shows our model achieves the state-of-the-art performance of multi-agent trajectory forecasting on heavy datasets. In the following, we show some qualitative results under challenging scenarios. The first case is a sequential prediction results under quick lane changing. The second case is waiting for the space for lane changing. Next, we demonstrate the sequential predictions when driving in moderate traffic conditions. as well as the sequential predictions when driving in congested traffic conditions. We also show the prediction results from the different agents under the same scene. In this cross-lane changing case, we respectively appoint the front, rear, and middle vehicle as the eagle agent to compare how the prediction results differ from each other. As our method could produce different futures by performing different plans under the same historical situation, we employ a model-based vehicle planner to generate diverse vehicle trajectories with different behaviors. Then our model could be evaluated from more simulated situations. We conduct a user study by comparing our generated results with the real situations to verify the rationalization of predicted outcomes. Each pair of videos are derived from a segment of 8-second traffic sequence recorded in the dataset. One video displays the complete recording of the real tracking data. The other shares the same history sequence but contains a different sequence in the last 5 seconds. The simulated results were selected as unreasonable with a rate of 52%. Near the same proportion indicates our model generalized well to different plans. With this planning prediction coupled pipeline, it's feasible to explore how to plan in different traffic situations actively. In the following, we illustrate some challenging scenarios with diverse future states produced by PiP given different Eagles plans. In the first example, we can see reasonable results from different driving behaviors. And more importantly, a potential collision could be forecasted when performing an aggressive maneuver for the Eagle agent. In the second example, we demonstrate diverse predictions when performing different plans under the same driving maneuver. Lastly, planning for lane changing behavior is more challenging when the vehicles go much faster. In this example, although rapid acceleration or deceleration becomes very risky, feasible planning still exists. All these examples further indicates that the planning prediction coupled pipeline is especially beneficial for planning in highly interactive scenarios. Thanks for watching. If you are interested in this work, please refer to our paper and project page for more details.